So we had a formula like this. Okay, this was the formula that we had used to obtain the reverse saturation current at a particular temperature when we have knowledge about the reverse saturation current at another certain temperature. So then we have seen that the diode current equation, okay, if you look at this diode current equation, we have to be careful that there are two temperature dependent terms here. One is the Vt, which is called the volt equivalent of temperature, represented by T upon 11600. But the other temperature dependent term, and which is mostly ignored, many times ignored by many students, that is I naught T, okay, the reverse saturation current. Because when we look at the equation of a diode, it looks as if the reverse saturation current is constant, okay, but you have to keep in mind that it's a temperature dependent term, and if in the question you are given a reverse saturation current at a certain temperature, like suppose 300 degree Kelvin, and you are asked to find the diode current at 400 degree Kelvin, then you need to find the new reverse saturation current at 400 degree Kelvin. Then only you can use this diode current equation. Otherwise, you will get a wrong answer. Then we have seen that what is an operating point. Okay. So we had taken a circuit like this, which had a power supply of 5 volt connected, which had a load resistor of 1 kilo ohm, and we also had this blue colored characteristic. Okay, this blue colored characteristic was available to us. Now we had to find the operating point of the given diode in this circuit, where the circuit parameters are V equal to 5 volt and RL equal to 1 kilo ohm. So what this we have obtained first of all a load line. Okay, this red colored line is called the load line, and that load line intersected with the characteristic at a particular point known as the operating point. Now, without making any calculations, okay, without making any calculations over here, we had come to know that what is the current through the diode and what is the voltage across the diode by dropping perpendiculars from this operating point on the x-axis and also a perpendicular on the y-axis. Okay, so that gave us the ID and VD. So we did not solve it, but we used the available characteristic of this diode, and then we just obtained 2 points on this x-axis and the y-axis, joined the 2 points, we got a line, and that line intersected with the characteristic over here, okay, and we called that as operating point. Then you have also seen the effect of changing the voltage supply. Suppose the voltage was increased to 10 volts, then you saw that we got a parallel line, this purple colored line. Okay, we got this purple colored line which was in parallel with the red colored line. Okay, so the effect of changing the power supply is that you get a new line which is parallel to the original line, and that resulted in a new operating point which was called as Q2. Then another effect that we had seen was that if we increase the load resistor, what would happen? Keeping the voltage equal to 5 volt, So you saw that this blue colored line, you're getting the light blue colored line, where the starting point of the line on the x-axis is the same, that is, it is having the coordinate 5 comma 0, but the end point on the y-axis is different because we have increased the resistance. So you can see that the when you change the load resistor, then the slope of the line is going to change. And as the slope of the line has changed, you get the line now intersects at a different point. So again, you get a new operating point, which is called the Q3. Okay. Then from this operating point, you then went on to find the static resistance of the diode. So what is static resistance? It is defined as the ratio of voltage across the diode to the current through the diode. So R1 is equal to VD1 upon ID1 is the resistance of the diode when the operating point is Q1. Similarly, if you find the ratio of VD2 and ID2, this will give you a new resistance, that is R2. And the another point is Q3 over here. Okay. Another point is Q3 over here. So that would give you R3 is equal to VD3 upon ID3. Okay. So what you can see is that there are three resistances available to you, and all of these are the resistances of the diode. Then my question is that out of R1, R2 and R3, which resistance is going to be the highest? Out of R1, R2 and R3, which resistance is going to be the highest? Can you hear me?
Yes, sir.
So out of R1, R2 and R3, which resistance is going to be the highest?
R2 सर,
R2.
क्योंकि सर वहां पर जाके स्लोप एकदम से बहुत ज्यादा चेंज हुई है सर, मतलब सर V
R2
की वैल्यू
मतलब
ज्यादा।
आप R2 मतलब ऑपरेटिंग पॉइंट Q2 की बात कर रहे हैं आप. You're talking about the operating point Q2 and the point is over here.
यस सर।
Okay. Anybody else?
Sir, R3.
R3. It's a question or is it an answer?
Sir, answer, sir, R3 is that blue.
Are you answering or you are asking question?
Sir, answer.
So you say that this is having the highest resistance. Anybody else?
Yes, sir.
So obviously you have taken the two extremes, so either Q2 or Q3. Q1 is lying between Q2 and Q3, so nobody is going to say that about Q1. Q1 is not going to be the choice. Okay. So this is your diode. So we are talking about this characteristic in the forward bias, and this is the characteristic in the reverse bias. And the question is that this is Q1, this is Q2, and somewhere here it is Q3. The question is that out of these three operating points, at which operating point the resistance of the diode is the highest? the question, is it clear? Question is clear to you? Yeah. This red line over here is the representing the complete characteristic of the diode which is available to you. Now you are getting the points Q1, Q2 or Q3. You are getting a particular point depending upon the specific value of the external voltage applied and the load resistor. Okay, for a specific value of load resistor and a specific value of the external voltage, you will be at any of these points, Q1 or Q2 or Q3. Okay, any point on this characteristic, you can be on any of the point on this characteristic. Okay, but in our case, we are having 3 points. So one is Q1, other is Q2, and this Q3. The question is that at which point the resistance is going to be the highest? Q2. Okay, so the answer is, ask you, what is the reason for taking Q2 as the choice? Huh?
Sir, slope is inversely proportional to 1 by R.
सर Q3 होगा ना, Q3 होगा सर.
Okay. See, देखिए, the answer is Q3. Q3 has the highest resistance. At Q3, the diode has the highest resistance. You need to understand, even if you don't know what is the resistor, what is the voltage supply, even if you look at the characteristic, okay, the characteristic of the diode, it simply says that, okay, if I can redraw it here, okay, I redraw it here. If you look at this characteristic, what does it tell you? Okay. You can choose any point on this characteristic, okay, you can choose any point on this characteristic, but if you see that, if when you are, suppose this is the cut-in voltage over here, okay, when you are somewhere below the cut-in voltage over here or like this, okay, when you are here, you know that for a given voltage, the amount of current that you are getting is less. Okay, for a given voltage, the amount of current that you are getting is less. Now, if I try to give values to this, then it is like this: 0.1, 0.2, 0.3. This is suppose 0.6. Then what you see is that this 0.6. Then if I make an equal distribution, then this is suppose 0.7. Now, if you look at this characteristic, then the highest point, if I drop a perpendicular from the highest point, and all of it lies, this whole characteristic over this region will lie between 0.6 to 0.7. So when you perform an experiment in the lab, you will not go beyond 0.76 or 75 voltage on the x-axis, and the current is increasing, but you will not go beyond 0.78 or maximum 0.8, you can say, in the forward characteristic. It means, what does it mean? With a small variation in the voltage in this region, you are getting a larger current. So which is good? Small voltage and more current means low resistance. So as you move on top of this characteristic, so if I move from here to here, the resistance is reducing. If I move from here to here, then the resistance is reducing. But if I move in this direction, resistance reduces. Okay. If I move from here to this direction, then the resistance of the diode increases. Because the answer is that for a given variation in voltage, you don't get much current increase when you are below the cut-in voltage. And that's why, if you look at this characteristic also, then it says that it's an exponential increasing characteristic. So if you are on top of this characteristic, if you are somewhere here, okay, if you are somewhere here, then you are having the lowest resistance of the diode. So the resistance of the diode is varying with the external voltage applied. Okay, so if you increase the external voltage, the voltage across the diode will increase. If the voltage across the diode increases, so you will be coming from the cut-in towards this low resistance region. Okay, so mostly you operate your diode in this region only, beyond cut-in. As I said, if you are operating the diode in the forward bias condition, in the forward bias region, then you always try to operate the diode in a region where the resistance of the diode is going to be less. So normally if you calculate this in the lab, so this static resistance, its value ranges from 30 ohms to 150 ohms. 30 ohms to 150 ohm, like this, depending on at which point on the characteristic you are. Okay. Any questions here?
Yes, sir.
Oh.
Sir, if we see the lines of Q2 and Q3, sir, then they are parallel, and it means that their slope will be equal. Sir, then why they have different resistances? Because we have seen that slope equals to -1 upon static resistance.
Yes. Now, what you are going to see is that when you drop a perpendicular from this point, okay, if you look at this point Q1, okay, this is Q1, so you are somewhere here, okay, but when you look at this point Q2, you are somewhere here. So the variation in VD1 and VD2 is less, whereas the variation in ID1 and ID2 is more. Can you see that? You're moving a very small distance over here, but you are, hello, क्या चल रही है? Okay, that's why you get a higher, smaller resistance when you move uh, along the increasing currents.
सर ऐसे तो सर अगर हम एक तरीके से देख रहे हैं तो कुछ और रिजल्ट आ रहा है और दूसरे से देख रहे हैं तो सर कुछ और आ रहा है.
तो कहाँ क्या होगा क्या इसमें? दिक्कत कहाँ है?
सर नहीं सर, आपने उस दिन बताया था कि स्लोप इक्वल्स टू
नहीं, ये तो
माइनस.
RL तो वो है ना, RL तो एक्सटर्नली कनेक्टेड रेजिस्टेंस है ये तो.
अच्छा सर, मतलब ये स्टैटिक रेजिस्टेंस नहीं है.
ना ये स्टैटिक कहाँ हुआ? RL है ना, ये तो लोड रेजिस्टर लगा हुआ है ना यहाँ तो.
ओके सर, मैं
ये
इसको सर स्टैटिक रेजिस्टेंस समझ रहा था.
नहीं, ये तो ये लोड रेजिस्टर है.
ओके सर,
ये
ओके.
RL फिक्स है आपका, लेकिन VD और ID तो चेंज होगा ना जब आप कैरेक्टरिस्टिक में मूव करेंगे.
ठीक है सर.
Okay. Now, what you see with the static resistance is that static resistance. Okay, the static resistance varies. Okay, it varies by a large value. It varies with operating point. It varies with the operating point. So, इसका variation, as I said, it varies from 30 ohms to 150 ohms. So, static resistance gives you an idea that for a given DC voltages and currents across the diode, what is its resistance? But in most of the applications, what happens is that you're going to use AC inputs. AC inputs are used. Okay, so like this is a diode. So what you have done till now, you had applied a voltage, DC voltage, and a load resistor RL. And we said that suppose this was 5 volts. What I'm saying now is that, okay, you have selected the operating point by applying this DC voltage. So when you apply a DC voltage of 5 volts, you know that you are going to be at the operating point Q1. You have selected the operating point. But most of the applications you will find that you will be using the AC inputs, which have to be modified or altered in some manner. So apart from this DC, you will be applying an AC input also. You will be applying an AC input also. Okay. So what happens is that now you suppose say that I have applied a certain AC voltage, and if I go back to this operating point over here, then this on the x-axis, when I used V equal to 5 volt, then I got an operating point at VD1 which was less than 5 volt. So you can say that whenever the diode is on, you will be approximately at suppose it is 0.65 volts. It is 0.65 volt. So what I'm trying to say is that you have applied a certain voltage. Now the voltage across the diode is, as you can see, it is 0.65 volt. Okay, but you're also applying an AC input. So what will happen is that, suppose this is your ground, and I make this as the y-axis on which you are having the voltage. Okay, this is ground. So I say that, so suppose this is 0.65 volt. 0.65 volts. What does it mean? It means I'm saying that the voltage across the diode is certain DC value, which is 0.65 volt. Now what I do is I say that, okay, let this AC be, that has been applied externally. It is such that, okay, it is such that its peak value is 0.05 volt. Its peak value is 0.05 volt. Okay. Okay. So what would happen now? It means I am having an AC signal, so it is 0.65 plus 0.05, so it will go like this, and 0.65 minus 0.5, so this will be giving me a 0.7 volt variation, and this will giving me a 0.6 volt. So due to the applied AC signal, the voltage across the diode, okay, the voltage across the diode is not fixed, but rather it is varying between 0.7 to 0.6 volts. Okay. So in this case, what we will see is that you will see that the operating point is varying between this 0.6 to 0.7 volts. It's varying. So this static resistance then will not be a useful parameter, because then you will say that, okay, the resistance of the diode is varying. Okay. So in that case, what you do is that you go to another resistance, which is called the dynamic resistance of the diode. Dynamic resistance of the diode, a more useful parameter as compared to the static resistance. So dynamic resistance is represented by small r, or it is also represented by capital R with a subscript F, known as the forward resistance. And this is defined as the change in the voltage across the diode upon the change in the diode current, where it is important that the changes are small. Changes are small. So what does it mean in the characteristic? If you look at this characteristic, I'm again going to redraw it. voltage across the diode, current. I'm redrawing it, so it is going something like this, So I've connected a certain DC. So when I connect a DC, I get a load line, and through that load line is suppose intersecting like this. So my operating point is somewhere here. This is the operating point. Okay. So from this operating point, now I drop a perpendicular on the x-axis. On the x-axis. Okay, so I get this voltage as VD. I also drop a perpendicular from the operating point on the y-axis. So it is going to give me this as, suppose ID, let's call this as let us leave it as ID and VD only. Now what we are trying to find out is that this is the VD, but as I said, that you are applying an AC signal, suppose, then an AC signal is going to vary such that it is varying somewhere between over here and somewhere over here. An equal variation. So that would mean that I am saying that the peak of the AC is like this. It's varying like this. Okay, it's varying like this. It's an AC signal. In that case, what you see is that now the diode voltage is varying between the 2 points. At one point, this I will call it as VD1, and this point I call this as VD2. Now, as I have drawn a perpendicular from VD1 on the characteristic, so from this point I also drop a perpendicular on the y-axis. So this will give me ID1. Similarly, from VD2 I had drawn a perpendicular on the characteristic. From this point I again draw a perpendicular, so this gives me ID2. So what I see is that the voltage across the diode is varying between VD1 to VD2, and the current is varying between ID1 and ID2. Now I apply the rule. According to the definition of the static resistance, this small r is going to be equal to change in VD, that is VD2 minus VD1, upon the change in current, that is ID2 minus ID1. Okay, so this is going to be a certain value. Suppose it comes as 25 ohms. Normally dynamic resistance is less, so this is coming as 25 ohms. Okay, so if you look at this, then it is actually nothing but a slope of the characteristic. You are actually obtaining a slope at this operating point, blue colored operating point. Suppose I call it as Q. So I'm trying to draw a slope like this. It is like this. So we are talking about a slope. So if I extend this slope, okay, it's going to look like this. I extend it and I intersect it with the x-axis. So I get a line like this. So when I say that the dynamic resistance is 25 ohms, it means I am saying that this is how it will be modeled, like a line, a straight line. Okay. So now I will be looking at the characteristic of the diode not as an exponentially varying characteristic, but as a straight line. as a straight line. Okay. Any questions here? Any questions here, students?
No, sir.
No, sir.
Okay. So you need to remember that all the electronic devices, whether it's a diode, whether it's a BJT or any other transistor, their characteristics are always going to be non-linear. Suppose I say that this is a non-linear characteristic. This is not looking straight. But what we say is that for a small, because when I said here, changes are going to be small. So you need to be certain that you are taking small partitions of the characteristic. So within this small partition, it is looking straight. Okay, this characteristic is looking like straight. Okay, so even if I draw a circle in front of you like this, if I draw a circle like this, now it is circular. But if I take small partition on it, okay, if I take a small partition, okay, like this, so within this partition, it is looking straight. That is the basis of most of all the electronic devices, because all the electronic devices are non-linear in nature. But what you do, you give an external biasing to select a particular point. The external biasing is a DC power supply. Okay, so you need DC supply. So with the help of a DC supply, you select a particular operating point. You say that, okay, I want to operate in this region. And then once you select an operating point, then you apply a AC. Then you apply an AC. And the variations will take place around this operating point only. So your AC is going to vary along this operating point. Okay. And again, this variation has to be small, because if I say that my characteristic is like this, okay, its characteristic like this, I have taken an operating point somewhere here, but I say that my VD is varying from here to here. And you can see that this is not a straight line, it is having a curve. Then you're not using the device properly. Okay, so you have to be careful that this variation must not be large. It must not be large. It must be a small variation. So when you perform the experiment in the lab, what most people do is, because you have got a characteristic, suppose like this. Now, many times students don't find the operating point. Okay, you got a characteristic, you don't find the operating point. What they do? They randomly select a particular point on the line, on the characters. They randomly select a particular point. Like this. Okay. No load line, nothing. You don't worry about the power supply. You just say that, okay, I have got a characteristic, so I want to find, I have been asked to find the static resistance. So हर स्टूडेंट जो है अपना अलग अलग पॉइंट लेगा. सपोज एक ही बैच में, एक ही ग्रुप में सबने मिलके एक रीडिंग लिया और सबका एक टेबल बना के कैरेक्टरिस्टिक भी सेम आया है, तो एक स्टूडेंट ने पॉइंट यहाँ ले लिया, दूसरे स्टूडेंट ने पॉइंट यहाँ ले लिया. ओके, तो Q1 Q2 और तीसरे स्टूडेंट ने पॉइंट यहाँ ले लिया. तो एक ही बैच में आप तीनों स्टूडेंट्स के आंसर्स अलग अलग आएंगे स्टैटिक रेजिस्टेंस के. तीनों स्टूडेंट्स के आंसर्स अलग अलग आएंगे स्टैटिक रेजिस्टेंस के. ओके, दैट विल बी द वेरिएशन. तो आप बोलोगे कि एक बोलेगा नहीं डायोड रेजिस्टेंस इतना है, दूसरा बोलेगा डायोड रेजिस्टेंस इतना है, नहीं थर्ड बोलेगा डायोड रेजिस्टेंस तो कम होगा. So from the same readings, if you don't select the same point, then you will get different static resistance. Now once you have selected, now suppose तीनों ने मिलके एक ही operating point को select किया, तीनों ने मिलके एक ही operating point को select किया. You suppose says that I have selected an operating point Q2. Okay. Selected an operating point Q2. अब क्या होगा? अब अगर सभी स्टूडेंट्स ने एक ही बैच के स्मॉल वेरिएशन रखा, यानी कि स्मॉल वेरिएशन, यू आर समवेयर हियर, यू मस्ट सी दैट योर कैरेक्टरिस्टिक मस्ट लुक लीनियरली. जो आपको, अगर आपको लगे कि मैं डिस्टेंस कहाँ रखूँ, कितना रखूँ, क्योंकि आप तो ऐसा नहीं कि आप AC अप्लाई करोगे, ऐसा कुछ नहीं करोगे. आप आपको डायनेमिक रेजिस्टेंस निकालने बोलेंगे तो आप एक स्टैटिक पॉइंट सेलेक्ट कर लिया, फिर आप एक पॉइंट ऊपर लोगे, एक पॉइंट नीचे लोगे, ओके, इस ऑपरेटिंग पॉइंट के. अगर किसी स्टूडेंट ने ज़्यादा वेरिएशन रखा, यानी कि यहाँ रख दिया और एक ने यहाँ रख दिया, तो ये आंसर गलत आएगा, यू गेट अ रॉन्ग आंसर. तो डायनेमिक रेजिस्टेंस अगर आप ग्राफिकली सॉल्व कर रहे हो तो आपको ये ध्यान देना है कि आप ऑपरेटिंग पॉइंट के बिल्कुल नज़दीक होने चाहिए, ताकि आपका जो सेक्शन ऑफ द कैरेक्टरिस्टिक है वो आपको विजिबली वो लीनियर दिखाई दे, स्ट्रेट लाइन दिखाई दे. अगर आप ऐसा कर रहे हो, लाइक दिस, यू ड्रॉप परपेंडिकुलर लाइक दिस, okay, you find this delta V, you find this delta I, and you put it in your equation R equal to delta V upon delta I. So आपका जो static dynamic resistance आएगा, that will be same for each of the students. Okay. So this must be kept in mind while trying to find the dynamic or the static resistance from a VI characteristic of a diode. Okay. Are you able to hear me? सुनाई दे रहा है?
Yes.
ओके. सो ये है स्टैटिक और डायनामिक रेजिस्टेंस. अब ये जो है, यही इक्वेशन जो है, आप ये जो आपने ग्राफिकली किया डायनामिक रेजिस्टेंस को, आप इसको एनालिटिकली यानी कि इक्वेशन के फॉर्म में कर सकते हैं. कैसे करेंगे? आपको डायोड का करंट इक्वेशन पता है, I इक्वल टू आई नॉट ई रेज टू वी अपॉन ईटा वी टी माइनस 1. तो आपको R निकालना है, R is equal to dV by di. What you do here is you differentiate it with respect to V. ये आ जाएगा di by dV is equal to 1 upon R is equal to, क्या आएगा डिफ्रेंसिएशन, I नॉट e raised to V upon ईटा वी टी, फिर क्या आएगा अपॉन ईटा वी टी, यही आएगा.
Yes, sir.
ओके. सो अब ये जो I नॉट e raised to V upon ईटा वी टी है, इफ यू लुक एट दिस इक्वेशन, व्हाट इज इट? यहाँ से अगर आप लेफ्ट हैंड राइट हैंड साइड देखो, I नॉट e raised to V upon ईटा वी टी इज इक्वल टू I नॉट e raised to V upon ईटा वी टी इज इक्वल टू I प्लस I नॉट, है ना? अगर मैं इस I नॉट यहाँ ले जाऊंगा लेफ्ट हैंड साइड में, तो आई विल गेट द सेम एक्सप्रेशन. तो ये जो न्यूमरेटर है I नॉट e raised to V upon ईटा वी टी, इसको हम कैसे लिख सकते हैं? इसको हम लिख सकते हैं I प्लस I नॉट अपॉन ईटा वी टी. Usually you are going to find this resistance in the forward bias region. So this I naught is going to be much smaller. I naught is negligible. I naught is negligible compared to the diode current I. Okay, so ये reverse saturation current है. So you can say that this is approximately equal to eta Vt upon capital I. Eta Vt upon capital I. This is the formula for the finding the dynamic resistance of a diode. If you want to find it with using a formula. Okay, so if you know that if you are given the forward voltage, suppose the forward voltage is the voltage across the diode is 0.6 volts, the temperature is known to you, then it's also given that whether it's a silicon diode or a germanium diode, आपको बस ये करना है कि इस डायोड करंट इक्वेशन से I निकालना है, यानी करंट निकालना है, यहाँ सब्स्टिट्यूट करना है, VT ऑलरेडी पता रहेगा, VT इज इक्वल टू T/11600 पता रहेगा, ईटा भी पता रहेगा कि वो सिलिकॉन है तो 2 रहेगा और जर्मेनियम है तो 1 रहेगा, सब्स्टिट्यूट करेंगे तो हमको डायनेमिक रेजिस्टेंस आ जाएगा विदाउट एनी ग्राफ. ओके, इज इट फाइन?
Yes, sir.
Okay. Now coming back to your characteristic, जब हमने डायनेमिक रेजिस्टेंस निकाला, okay, I will go back to the characteristic. हमारा characteristic कुछ इस तरीके से था, like this. Okay. हमने डायनेमिक रेजिस्टेंस निकाला एक पर्टिकुलर ऑपरेटिंग पॉइंट पे, उसको जब निकाला तो हमको एक स्लोप मिला, हमने स्लोप कुछ इस तरीके से मूव हुआ, ऐसे यहाँ गया, फिर हमने इसको एक्सटेंड किया, ये यहाँ नीचे आके इसको यहाँ इंटरसेक्ट कर गया. तो ये जो है इसको हम ऐसे देखें अगर, सो आई कैन रीड्रॉ दिस. अब मेरा जो ध्यान है, सो आई विल बी लुकिंग एट not the whole characteristic of the diode which is green in color, but I will be just looking at the purple colored line. So in that case, if I just think of the purple colored line, then this characteristic of the diode is actually like this. You wait till the cut-in voltage, then there is a slope. Okay, there is a slope like this. This straight line. Okay. अब मेरा पूरा कैरेक्टरिस्टिक जो है ये ग्रीन कलर ना होते हुए अब हम इसको डायोड को ऐसे देखेंगे, where this slope is 1/RF, the forward resistance of the or the dynamic resistance of the diode. On the y-axis is ID, on the x-axis is VD. तो अब हमारा डायोड जो है, अब हम एग्जैक्ट मॉडलिंग नहीं करेंगे, अब ये हम बोलेंगे डायोड का हमने मॉडल कर दिया. And the diode is not considered as that exactly that which is represented by the green colored line, but it is represented like this, जहां एक कट इन वोल्टेज है V गामा. ठीक है, तो अब ये जो डायोड था आपका ओरिजिनल जो डायोड था, ओके, इसको आप मॉडल करेंगे विथ अ कट इन वोल्टेज की एक कट इन वोल्टेज होना चाहिए प्लस एक फॉरवर्ड रेजिस्टेंस होना चाहिए R, या फिर इसको हम कैपिटल R स्मॉल f भी बोलते हैं. और जब हमने इस डायोड से इन दो चीजों को अलग से रिप्रेजेंट कर दिया तो ये जो डायोड है अब हम इसको बोलेंगे इट्स एन आइडियल डायोड. ठीक है, दिस इज कॉल्ड द पीस वाइज. ओके, दिस इज कॉल्ड द पीस वाइज मॉडलिंग ऑफ डायोड. यानी कि हम इसकी बात कर रहे हैं कि हमने रेजिस्टेंस को कंसिडर किया डायोड के, जिसको हमने स्मॉल r से रिप्रेजेंट किया, हमने कट इन वोल्टेज को कंसिडर किया डायोड के, जिसको हमने V गामा से रिप्रेजेंट किया. तो जो बचता है यहाँ जो है हम इसको हम एक आइडियल डायोड मान के चलते हैं. तो आइडियल डायोड विथ दिस टू पैरामीटर्स इज कॉल्ड पीसवाइज मॉडलिंग ऑफ अ डायोड. अब ये हमारा कंप्लीट मॉडल है एक डायोड का. जरूरत पड़ने पर हम डायोड को पूरा ऐसे एज्यूम करके चलते हैं, या फिर मान लो आपके सर्किट में एक रेजिस्टर लगा है. ओके, जैसे कि इफ आई गो बैक टू दिस सर्किट, ओके, दिस इज माय सर्किट. load resistor is there, and there is certain AC supply and some DC voltage, okay, like this. अब यहाँ पर ये जो डायोड है, okay, I have to model it. अब मैं इसमें से किस पैरामीटर को रखूंगा, it will depend upon what are the voltages and what are the load resistances in the loop. Suppose इस RL का वैल्यू है 100 ohms, और ये जो डायनेमिक रेजिस्टेंस है डायोड का, सपोज इट इज 40 ohms, okay, and the external supply is also not high. It is, suppose this DC supply is suppose something like 1 volt. So since this 1 volt is not very less as compared to the cut-in voltage of a diode, which is 0.6, so I cannot ignore this 0.6 volt, यानी कि कट इन वोल्टेज को मैं इग्नोर नहीं कर सकता as compared to this power supply of 1 volt. तो मुझे इसको लेना पड़ेगा. Similarly, the dynamic resistance of the diode is 40 ohm, which is not very less as compared to the load resistor, which is of 100 ohm. बहुत कम नहीं है ये. तो इसीलिए मुझे अब क्या करना होगा कि जब मैं इस सर्किट को एनालाइज करने बैठूंगा, when I sit and analyze this circuit, so what I will do is I will replace this diode with the ideal diode. I will replace it by its cut-in voltage and also a series resistor that is small r. Now this is going to be capital RL, this is going to be my AC supply, and this is going to be my external supply 1 volt. क्योंकि मेरे दोनों वोल्टेजेस और लोड रेजिस्टर्स कंपेरेबल थे डायोड के पैरामीटर के से, so I cannot ignore these two values. इसलिए मुझे मॉडलिंग करते वक्त, एनालिसिस करते वक्त इन दोनों को लेना पड़ रहा है. But at the same time, suppose I say that RL is equal to 1 kilo ohm. So 1 kilo ohm is 1000 ohm and the dynamic resistance of the diode is 40 ohm. 40 ohm can be neglected in comparison to 1 kilo ohm, which is 1000 ohm. So in that case, I model this diode as an ideal diode along with a cut-in voltage, and I remove this dynamic resistance of the diode. So I'm only worried about the load resistor, the power supply, and the external supply of 1 volt. Then I say that, okay, if the power supply is also high enough, if the power supply is, suppose, if externally applied power supply is suppose 10 volts, in that case, the cut-in voltage of 0.6 volt is not comparable to the 10 volts. यानी कि जो इस वोल्टेज हम ऑपरेट कर रहे हैं वो इतना ज़्यादा है कि डायोड के कट इन वोल्टेज से हमको कोई खास मतलब है ही नहीं. So what you do then is you also remove this power supply, this cut-in voltage which is represented by DC power supply, इसको हम हटा देते हैं. तो अब हमारा जो सर्किट है एक आइडियल बन जाएगा. एक डायोड है, एक RL है, एक AC है और एक एक्सटर्नल वोल्टेज है 10 volts का. So what I am trying to tell you is that depending on the circuit parameters, whether it's when you look at the voltage or when you look at the load resistor, you try to simplify your diode representation or the modeling as easy as possible. You try to represent it in a very easy manner for the easy analysis. जहाँ चाहते हैं आप कोशिश करें कि ज़्यादा से ज़्यादा पैरामीटर को आप इग्नोर कर सकें. और रेजिस्टेंस ज़्यादा है तो डायनेमिक रेजिस्टेंस को हटा दो, उसको मत कंसिडर करो. अगर एक्सटर्नली पावर सप्लाई ज़्यादा है तो कट इन वोल्टेज को कंसिडर मत करो. सो व्हाट आई एम टेलिंग यू इज दैट एक एनालिसिस करते वक्त ये आपके ऊपर डिपेंड करेगा कि आप अपने एनालिसिस को कितना सिंप्लीफाई कर सकते हो और इजी एनालिसिस कैसे कर सकते हो ताकि आपका एनालिसिस भी करेक्ट रहे, ओके, और आपको टाइम भी ज़्यादा ना लगे फॉर डूइंग दैट एनालिसिस. So I will stop here.